Let's just start off with a warm-up problem. This is actually one of the homework problems, but I don't think I assigned it. So warm up. If is the identity matrix, then AC is the identity matrix. If CA is the identity matrix, then AC is the identity matrix. Okay, and so this is basically saying that there's no one-sided inverse. Okay, right? If something works as the inverse matrix from the left side, then it's going to work as the inverse matrix from the right side also. There's no left-sided inverse matrix that only works on the left-hand side. If this guy works as the inverse on the left side, it's going to work as the inverse on the right side as well. That's not always true, but for us, it is true. So, and here's a hint. The hint is to show C is invertible. Just to get your brains going, if they stop. Morning. So we're doing a warm-up exercise. So I want you to think like this. What if you knew that C was invertible? Suppose you knew that already. Would you be able to finish it off? So see how you can get, if you have that, see how you would finish it off, and then think about how you could get it. I don't want to spend too much time, so just think for another minute and then we'll talk. Okay, talk to each other. Say something to your neighbor, even if it is, I have no idea. Zia, talk with Dan. Dan's trying to talk to me.
That's what I was thinking too. Like, and then C would be A's inverse, which is like A's inverse. And then turn it out. As far as I know. That's fair. Is that what you're thinking?
Okay, anybody have an idea? Anybody have an idea? Either part of it? Like suppose you already have this, that C is invertible. How would you get to the end? Julia, go ahead.
I I would just multiply both sides by C inverse.
Yeah. So if you had that C was invertible and you had this fact, you would just say, well, look, CA is equal to I, so C inverse CA is equal to C inverse I, right? And that means that A is C inverse I, and then where would you go from there? You multiply on the right-hand side, you multiply by C, right? So you multiply by C inverse on the left-hand side, and you take your equation, you multiply on the left-hand side by C inverse, you get to here, and then you multiply that guy on the right-hand side by C, and that would give you that AC is equal to the identity. So if you had that C was invertible, then you'd be okay. Dan, yeah?
So for the invertible part, is it enough to show that C is invertible that there is some matrix A such that C times A equals 100?
No, you need, so to show that something's invertible, to find the inverse, you have to show that there's a two-sided inverse. Okay, so you can't just say, well, look, you've got a right-sided inverse, so C is invertible. That'd be too easy.
And so the first step there is still showing that since you have C, A equals I, that A is C inverse.
We want to show that, so if we have that C is invertible, then we're home free. Okay, so let's show, can anyone show that C is invertible? That's what we need to do, show that C is invertible. Anybody have an idea? Lizzie, you're twitching?
No.
No? Okay. Okay, hint is, look at the determinant, use the determinant. What do you know about the determinant and invertibility? Russ?
So, if C times A is equals to I, so we can regard A as En times En minus 1 times to E1. And the addition matrix is invertible, which means the determinant is non-zero, and the identity matrix determinant is non-zero, which means C must be non-zero.
Okay. So you've sort of got it. You've made it a little bit more. I think you've. So you say, okay, well, look, we know that the determinant of CA is the same thing as the determinant of I, right? Which is 1. Right? The determinant of the identity matrix is 1. Right? Well, what do you know about the determinant of CA? Of a product?
You can split it.
You can split it, right? This is the determinant of C times the determinant of A. Right? Okay, so you've got this times this equals 1. So neither of them could be 0. Neither of them is 0. Right? So you know that the determinant of C is non-zero, and we had that theorem saying that if the determinant, the invertibility is the same thing as your determinant being non-zero, right? So that was one of our results, that a matrix is invertible if and only if the determinant is non-zero, right? Okay, so that does it for you, right? Okay, so C is invertible. So normally I grade it up a bit more carefully, but I want to get on with the lesson. Okay, that's just to get you going. So a couple of things that I wanted to cover. So there's a couple of last things that I want to cover that will be fair game on the exam. Okay, so just some small things. One is this thing from 2.3. Called the Adjoint Matrix. And the Adjoint Matrix, the way you want to think about it is you want it has to do with the wrong cofactor lemma. So recall the wrong cofactor lemma. Okay. Anybody anybody remember, I hope you all remember the cofactor lemma, right? It says that if you take the entries from one row and the cofactors from another row, take the entries from row I and the cofactors from row J, you have some matrix, right? So A is some n by n matrix, right? A is some n by n matrix. Then you take the dot product of the entries against the cofactors. Well, you end up with 0 if they are from different rows, and you end up with the determinant of A if they're from the same row. Right? Everybody okay? You better remember. I hope you know this. You should. Okay. So we're going to write that in a different way using something called the adjoint matrix. Okay. So again, we have this n by n matrix. We define the adjoint matrix of the matrix A by, and we denote it adj A. We define it to be the matrix of cofactors. Okay, it's going to be the matrix of cofactors A11, A12, A13 through A1n, AN1, AN2, ANn. Right? So it's a matrix of cofactors but transposed. Okay, the transpose of the matrix of cofactors. So you took, right, if you just took the normal cofactors, they would look like this, AN1, ANn, right? You take the transpose of that. Okay, and that's the adjoint matrix. Okay? Everyone all right? Okay, great. So, okay, so now, what happens if you take A times its adjoint? What happens if you take the matrix, your original matrix, and you multiply it by the adjoint matrix? Does anybody know? Did anybody read this? Anybody read it? Avery? No?
I
You
did
can?
read it, but I
don't remember?
don't remember.
That's okay. Yes.
Wait, I might be remembering the wrong part of
That's
the
okay.
chapter. Is it 1 over the determinant of A, or is that's a different part?
You're a little bit ahead. So go back a couple pages and then yes. Go back one page or so. See it?
You have to diagonal matrix of all the determinants plus the diagonal matrix.
Exactly. You're going to get a diagonal matrix. You're going to get a diagonal matrix with the determinant down the diagonal. In other words, you get the identity matrix, but multiplied by the determinant. You get the identity matrix multiplied by the number, the determinant. Okay, and this goes to what Avery was saying, so I wasn't going to say this so soon, but let me say it anyway. So, A times 1 over the determinant of A times the adjoint matrix is the identity matrix. Right? When I take A and multiply it by this thing, I get the identity matrix. Right? Multiplying both sides by 1 over the determinant gives me this equality. Right? Right? And what does that tell you? What does that tell you? This is the inverse, right? That tells you that this guy, the adjoint matrix, the transpose of the matrix of cofactors divided by the determinant is actually your inverse matrix, right? So the inverse matrix actually has a very specific meaning, right? It's the transpose of the matrix of cofactors, right? So A inverse is 1 over the determinant of A times the adjoint matrix. When you first calculated your inverse matrices, you may have thought, it seems kind of arbitrary. How do you figure out what is this thing, the inverse matrix? It turns out to have a very, almost geometric meaning. Okay, so let's explain this. So this is the observation, observe. And here, let's explain why. Why is that true? Well, if you take the matrix, take your original matrix, and you multiply it by the transpose of the adjoint matrix. I'm sorry, the transpose of the cofactor matrix. Multiplied by the transpose of the cofactor matrix. What happens? Everybody take half a minute and satisfy yourselves that this is what happens. So think about it or do it. Look at it. Okay, is it clear? Clear? Right. I hope you all saw what happened. Right? When you multiply, when you start multiplying, right, what's the one entry? Well, it's going to be the first row against the first column, right? And you see that you get A11, capital A11, A12, capital A12, blah, blah, blah. That's the expansion of the determinant, right? So you get the determinant, right? If I take first row, second column, I get A11 against A21, blah, 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 A1n to A2n, right? That's going to be 0 by the wrong cofactor lemma, right? That's going to be 0, and we get zeros throughout, right? On the second row, right, I'm going to get, second row, first column, I get 0. Again, the wrong cofactor lemma. When I take the second row against the second column, you see that I get the determinant. Etc. You see what's going to happen. Right? You see what's going to happen. Okay. So this is the adjoint matrix. This is the adjoint matrix. Everybody get some idea of it. What's the adjoint of ABCD? What's the adjoint matrix of ABCD? Well, you need to take the cofactors. Well, what are the cofactors? Take the cofactors and transpose them. Cofactor here, you're going to get negative 1 to the 1 plus 1 times the determinant of the minor. That's D. Right? Over here, you're going to get negative 1 times the determinant of the minor, negative C. Here you're going to get negative 1 times the determinant of the minor, that's negative B. Here you're going to get 1 times the determinant of the minor, that's A. Right? And so you take the transpose of that, and you get D, negative C, negative B, A. Right? And then you take, so the inverse of a 2 by 2 is always going to be 1 over the determinant times this, D negative B. Right? Which is a formula you may have seen in high school. So just as an example of how you can use the adjoint matrix to get the inverse matrix. Okay. But I should say that this is not really a good way to get the inverse matrix. Right? It's not any faster than the other way of doing it. Right? If you have to calculate the cofactors, right, that involves taking determinants. Right? It's not computationally better. Okay. Okay, let's go on. So that's all I wanted to say from 2.3. There is something called Cramer's rule in that section, but I don't think it's worth talking about because it's not that great. Okay. Okay. So is everybody all right? You guys seem kind of dispirited. You look like you're from
Season.
What?
It's a midterm season.
Midterm season. Okay, that'll do it. This is sort of, you look like the stereotypical student from the University of Chicago. But they all sort of stared at the ground. They trudged around staring at the ground. Yeah, they looked more like graduate students. Okay, so I'm hoping that you all watched the lecture for vector spaces and got up to the point where we're talking, we had gotten into 3.2 subspaces. And probably the main thing that you want to get from that part is that is the theorem that any non-empty subset of a vector space is a subspace if and only if it is closed under vector addition and scalar multiplication. The two properties, the two operations of the vector space. Right? Right. So the vector space, remember, has two operations. You can add things together and you can multiply them by numbers. Right? You can add them together, you can multiply them by numbers. Nothing about multiplying them by other vectors. Okay, just you can add them. You can add vectors and you can multiply by scalars. Okay, and this is the main thing that you probably wanted to get out. Probably should have gotten out of it. That the way to check if something is a vector space is to check if it's closed under vector addition. In other words, when you add things together, you stay in the set. When you multiply them by scalars, you stay in the set. Okay, so as long as those two things happen, then you can say your set is a subspace. So, okay, so let's do an example. Actually, this is not an example. Let me introduce another definition. This is the thing that I do consider fair game for the term. The notion of null space. Okay, so we define the null space N of A. Okay, so you have some matrix, need not be square. You have some matrix, some m by n matrix. We define the null space of A. The null space of A is anything in the domain, anything in Rn such that Ax equals 0. Okay. Anything that the matrix sends to 0. When you multiply it, you get the 0 vector.
I'm sorry, anything in the domain that sends what to 0?
That A sends to 0.
Okay.
Okay. When you multiply it by A, it turns to 0. Okay. So, if I have some matrix, 1, 2, 3, 4, 5, 6 again, right? Then this is a 2 by 3, right? And if I multiply something by it, and I get the 0 vector, then that ABC is in the null space. Okay, so concrete example, right? And so any ABC that solves the above is in the null space of the matrix 1, 2, 3, 4, 5, 6. Okay, so anything that solves the homogeneous equation. Okay. Yeah, Lizzie.
So the only null space for invertible matrices is 0?
That's right. Yeah, so that's actually one of your homework problems, I think. Which you've already basically solved. The homework problem is show that something is invertible if and only if the null space is 0. So show that a square matrix is invertible if and only if the null space is 0. But the null space being 0 means that the homogeneous problem has only one solution. Right, so that's it. Okay, well, sorry, let me go backwards a little bit first. So, null space. Null space is just anybody in the domain that the matrix kills. Okay, the matrix annihilates. Okay, sends to 0. Okay, so the question is the null space a subspace? Is the null space a subspace? So you have to check two things. Is it closed under vector addition? Is it closed under scalar multiplication? Right, so let's check. One, closed under addition. Is it closed under addition? In other words, if U and V are in the null space, is U plus V still in the null space? Is U plus V still in null space? If each of U and V get killed by the matrix A, does U plus V get killed by the matrix A? Think for 20 seconds. If AU and AV are both 0, is A times U plus V equal to 0? Absolutely, right? Absolutely, right? Right. If U and V are in the null space, in other words, AU equals 0, AV equals 0. Is U plus V in the null space? In other words, is AU plus V equal to 0? And the answer is definitely, right? Because, yes, so yes. AU plus V equals AU plus AV, right, by distributivity. Right? And so you get 0 plus 0, right, which is just a 0. Right? Okay. Okay. Right, so part 2, closed under scalar multiplication. Right? In other words, if U is in the null space, is alpha U in the null space? Or any alpha in your set of numbers? So write down something in the next 20 seconds. Like, how would you argue about that? Okay, turn to somebody nearby and say, you would say this. Okay. So the answer is yes, right? Right? The question is, if AU equals 0, does A alpha U equal 0? Right? That's what this translates to, right? If U is in the null space, in other words, AU equals 0, is alpha U in the null space? In other words, does alpha AU equal 0? Right? And the answer is yes, right? Because alpha AU is going to be alpha A. Right? I'm saying A alpha U is going to be alpha AU, which is just alpha times 0, which is 0. Okay. Okay. I hope this is pretty straightforward. Right? It should be. Right? Just checking these links. Okay, let me do a concrete example. So a concrete example, somebody gives you a matrix A, and it's some huge matrix. Okay, I'm not even going to write it down. Okay, but this matrix reduces to the matrix 1, 0, 5, negative 3, 0, 1, 2, negative 1, and then a bunch of zeros afterwards. So 0, 0, 0, 0, 0, 0, 0, 0. So I have some matrix here. Anyway, whatever it is, it reduces to this guy. Okay. So, sorry, maybe I should write it down. Why am I so lazy? 1, negative 2, 1, negative 1, 2, negative 3, 4, negative 3, 3, negative 5, 5, negative 4, negative 1, 1, negative 3, 2. Okay. question is, what is the null space? What is the null space? So somebody asks you, the null space is a subspace. Well, what is it? So you're basically asking, what's the solution set of, what's the solution set of AX equals 0? Right? Well, we've been doing this all along, right? We've done this many times. We didn't use this language, but we've done this many times already. So we don't really need to. So how would you do it? You use your Gauss-Jordan reduction, come down to here, right? And you'd say, okay, this is the same thing, right? So the system that we're looking at is x1 plus 5x3 minus 3x4 equals 0. x2 plus 2x3 minus x4 is equal to 0. Right? And then you write down what the solution looks like. So any solution must be of the form something that looks like this, right? x1 has to be negative 5x3 plus x3x4. x2 must be negative 2x3 plus x4. And x3 and x4 can be whatever they want. Right? Those are the free variables. Right? I hope you remember this. It seems it's trivial, but we need this. We need to be able to do this. We need to be able to do this now because we're going to need to be able to do this later. So where x3 and x4 can be anything. Any numbers. Okay. Another way of writing that is that the set of solutions looks like this. x3 times the vector negative 5, negative 2, 1, 0 plus x4 times 3, 1, 0, 1. Right? Where x3 and x4 can be any numbers. Right? I just wrote the same thing. Right? This thing. I just expanded this out as this. Right? Negative 5x3 plus 3x4, blah blah blah. That's the same thing as this thing here. Just by vector addition and scalar multiplication. Everybody okay? Nico?
We get the x3 and x4 on the bottom, and then over there when it was just 0. Oh, it's just because x3.
x3 and x4 can be whatever. x3 is x3 and x4 is x4. Right? So here we have x1 is this, x1 is this on the other side, x2 is this, x3 is x3 and x4 is x4. Right? Those guys are the free variables.
How do we know that again?
You missed the first part of the course. Come in later. I'll tell you. Yeah. But basically, when you're solving these sorts of equations, you have the lead variables and you have the free variables. The lead variables you express in terms of the free variables, and then the free variables can be themselves. Okay. But I can tell you more later. Okay. Everybody okay with going from here to here? Any questions of going from here to here? Okay, so I could actually rewrite this. Instead of x3 and x4 can be anything, right? So I'm just going to call these alpha and beta. I don't need to call them x3 and x4. Right? It's just anything that looks like this. Alpha times this guy plus beta times that guy. right? Some number times the first guy plus some number times the second guy. There's no need to call them estimators for. Okay. So what is this? What is this thing here? Anybody? There's a term for this sort of set. Do anybody remember this? In your review for the exam on Friday. The set of all linear combinations. Stella? Span, exactly. Right. So this is we call this thing the span of these two vectors. We define it to 0, 3, 1, 0. It's a span. Okay. So just to remind you, right? The span. So if you have given some vectors v1 to vn in a vector space V, then the set of all linear combinations C1 v1 plus C2 v2 plus Cn vn, right, where Ci are all real numbers, is called the span of the Vi. Like the span denoted span. Now, I know that we defined this only for Euclidean vectors before, right? We were talking about Euclidean vectors in Euclidean space. Euclidean space, right? Rn. Right? We were talking about real vectors before, but this same definition holds in abstract vector spaces. Some linear combination of your vectors, whatever your vector space is. So the null space, if you work it out, this sort of null space, if you work it out, it turns out you can express it as a span of these two vectors. Any questions? Any questions? Okay. I have an exercise for you, which is show that the span of some set of vectors is a subspace. Show that the span is a subspace. So remember what you have to do. There are two things you need to show: closed under vector addition and closed under scalar multiplication. So think, if you have something in the span, so let's talk this one. Okay, let's talk this one through. If you have something, let's think about closed under addition. If you have something in the span that is a linear combination, and you have another thing in the span that's another linear combination, and you add them together, you get something in the span? Sure. In other words, if you have a linear combination and you add on another linear combination, do you have a linear combination? Sure. Right? Right. If I have C1 v1 plus C2 v2, and I have some other guy d1 v1 plus d2 v2, and I add them together, I'm going to have C1 plus d1 v1 plus C2 plus d2 v2. Right? That's still going to be a linear combination. The sum of linear combinations is still going to be a linear combination.
So what that reminds me of is the first thing that we did, which was the 3 rules of how to like when you can add, when you can, to get a solution set, when you can add like two of the rows of a vector, or not of a vector, of a matrix, is that like similar to why that's okay, or are they completely different?
It's different actually, because here we're just saying that, well, look, if you have a linear combination and you add on another linear combination, it's still a linear combination, right? That was talking about, you know, how the solution set doesn't
But
change.
it's no kind of pattern or anything.
I don't think so. I don't think so.
Because it would be the same thing with the second part too, that you can multiply in a value alpha or beta, which is one of the things as well, which is that you can multiply a line.
Okay, yeah, you know, no, that's right actually. Yeah, that's right. Yeah, there is a pattern that these things are linear, right? You can add them and you can multiply them. That's right. Okay, so second one, is it closed under scalar multiplication? Right? If you have a linear combination and you multiply it by some number, is it still a linear combination? Sure, right? Because if you have, again, you know, some linear combination of these two vectors, and you multiply it by some number, well, then you're going to get, it's again, just a linear combination, right? So multiplying a linear combination, still going to be a linear combination. So it doesn't change it. Okay, so showing that the span is a subspace is pretty straightforward. Okay, there are some exercises. There's some exercises about the span that I think are not particularly great, but let me show you an example of it. So here's a typical exercise from the book. Does the span of these three vectors 1, 0, 1, 1, 1, 0, 0, negative 1, 1 equal r cubed? Does it equal r cubed? R3? Right. In other words, does the span of these three vectors give you the whole vector space? Right? Right. So this is asking, is everybody in the vector space expressible as a linear combination of these three vectors? Okay. So in other words, the question is, can any vector ABC in R3 be expressed as some linear combination, x1 times the first guy plus x2 times the second guy plus x3 times the third guy. Can any vector in R3, can every vector in R3 can be expressed as some linear combination? And you see that this is a question that we basically asked before, right? This is the same thing as asking, what? Can we find x1, x2, x3 to solve this? So 1, 1, 0, 0, 1, 1, 0. The question is the same thing as, can we solve this? For any ABC in R3? How would you answer that question? how do you answer this question? Like, can we solve this? How do you figure out if you can find a solution to this? Well, you just do Gauss-Jordan reduction. Right? You just do Gauss-Jordan reduction. something with, you know. Normally I hold my breath until somebody gives the answer, but there's no time for that. So yeah, so you just do the Gauss-Jordan reduction, right? You say, okay, take 1, 1, 0, 0, 1, negative 1, 1, 0, 1, ABC. Right? You do your Gauss-Jordan reduction, blah, blah, blah. Right? You'd end up actually with this result, 1, 0, 1, A negative B, 0, 1, negative 1, B, 0, 0, 0, C minus A plus B. Okay. Okay. That would tell you that the answer is no. Right? The answer is no. Because for this to work out, you need C minus A plus B to be 0. Right? If C minus A plus B is 0, then you're okay. But if C minus A plus B is non-zero, what you're saying is that 0x1 plus 0x2 plus 0x3 must be something non-zero. Right? So the answer is we cannot express everything. Right? If C minus A plus B is non-zero, then no. Right? We don't get the whole space. Okay, that's it for today.